Hi everyone, now we are going to discuss about asymptotic notation. In algorithm analysis, it is important to compare the efficiency of different algorithms. Instead of measuring execution time on a specific computer, we use mathematical notations called asymptotic notations. So these notations help us describe how an algorithm's running time grows as input size increases. In algorithms, efficiency is mainly determined by the order of growth of its running time. Here, T of n represents the running time or the number of basic operations performed by an algorithm. The function g of n is used as a reference to compare the growth rate. The asymptotic notations allow us to compare different algorithms without considering hardware speed or programming language. The three most commonly used asymptotic notations are big O, big omega, big theta. So there are three standard asymptotic notations. Big O represented as big O of g of n, which gives the upper bound of the running time. It represents the maximum growth rate. Big omega represented as omega of g of n, which gives the lower bound of the running time. It represents the minimum growth rate. Big theta, it represented as theta of g of n, which gives both the upper bound and lower bounds. It represents the exact order of growth. So these notations help us compare algorithms based on their efficiency. Big O notation. So the Big O notation describes the upper bound of an algorithm's running time. It tells us the maximum amount of work an algorithm may perform for large input sizes. So mathematically, T of n belongs to Big O of G of n if there exist positive constants C and n naught such that T of n is less than or equal to C into G of n for all n greater than or equal to n naught. For example, 100 n plus 5 belongs to big O of n square because for sufficiently large values of n, the function is always less than some constant multiple of n square. So big O notation is widely used to describe the worst case performance of algorithms. Big omega notation, it represents the lower bound of an algorithm. It tells us the minimum amount of work the algorithm must perform. Mathematically, T of n belongs to omega of g of n if T of n is always greater than or equal to C into g of n for sufficiently large values of n. For example, n cube which belong to omega of n square because n cube always grows faster than n square. Big omega is commonly associated with best case analysis. So big theta notation. So big theta notation provides the exact order of growth. A function belongs to big theta of g of n if it is bounded both above and below by constant multiples of g of n. In other words, c2 into g of n is less than or equal to t of n and it is less than or equal to c1 into g of n for sufficiently large values of n. For example, n multiplied by n minus 1 divided by 2, which appears in many sorting algorithms, belongs to theta of n square. So theta notation gives the most accurate description of an algorithm's complexity. So another method of comparing functions is the limit-based approach. We calculate the limit of t of n divided by g of n as n approaches infinity. If the limit is 0, then t of n grows slower than g of n. If the limit is a positive constant, both functions have the same order of growth. If the limit is infinity, t of n grows faster than g of n. Sometimes L-Hopstall rules is used to evaluate these limits. So this approach provides a mathematical way to determine asymptotic complexity. A basic efficiency classes. So this table shows the common efficiency classes used in algorithm analysis. Big of n is constant time where execution time does not depend on input size. Big of logarithm n, it is a logarithmic time commonly seen in binary search. Big of n log n, which is used by efficient sorting algorithm like merge sort and also quick sort. Big of n square is quadratic time usually found in algorithms with two nested loops. Big of n cube is the cubic time which appears in algorithm with three nested loops. Big of 2 power n is exponential time and is used in many recursive algorithms. Big of n factorial is a factorial time and appears in problems that generate all possible permutations. As we move down the table, the algorithms become increasingly slower for larger input sizes.